let's see what this linspace does. So if I print torch linspace 1 to 10, we go 1 to 10 with 5 steps in between, equal steps in between. Then let's see torch.log and torch.exp. So we have this tensor 1, 10, and 100. So what torch.log will do, you see these numbers 0, 2.3, 4.6. So e to 0 is gonna be 1. So torch.log will find which number. When you say e to this number, you get this number. So it will find logarithm, natural logarithm of this number. So e to 0 is 1, e is Euler's number, 2.7 something. And then e to 2.3 is 10, and e to 4.6 is 100. So it will just find natural logarithm of x. And then exp is reverse of log. So you will just put e to these logs. So you see exp of log of x. So if you do this, you will just get the same, because those are two reversing operations that get the same result in the end. So exp of log, so you will put this e to 0 is 1, e to this is 10, e to this is 100. Now we are trying to understand this line of code in this sinusoidal embeddings. So when it calculates frequencies with torch.exp, torch.linspace, torch.log, and this stuff. So we are trying to understand this line. So we want frequencies to grow exponentially. For example, 1, 2, 4, 8, 16, 32, etc. But linspace gives linear steps. So we take log of A and log of B. So those are starting and ending points in the linspace, A and B. From where to where does linspace go? Make linear steps between them, and then apply exponential to get exponential steps again. Let's see on an example how that works. So we want to make 6 different numbers between 1 and 1000, but we don't want them to be linearly spaced. We want them to be exponentially spaced. So this is the result that we want. You see here, this is 1, this is 3.9, this is 15, this is 63. Because of this means this number times 10 to 1. So this is 63, this is 251, this is 1000. Because it's 1 times 10 to power of 3. So it's growing exponentially, so that's what we want. Okay. So we take linspace from log of A to log of B. So from log of 1 to log of 1000. So that's gonna be 0, log of 1 is 0, to log of 1000 is 6.9. And we take 6 steps. And now we just exponentiate them, exponentiate these. So we get back our from 1 to 1000. And it's exponentially growing exponentially because we are literally using this linear space as exponents to the exponential function. So that's why it's growing exponentially. So let's summarize again. We want to create 6 numbers between this range, but they should grow exponentially. So instead of using linspace to calculate the numbers, we use linspace to calculate the exponents. So they grow exponentially later. So to calculate exponents, we don't calculate them from 1 to 1000, we calculate them from 0. So we just calculate exponents. So the first exponent should get us this one. The last exponent, e to the last exponent, should get us 1000. So we actually just calculate exponents in this linspace. And when we use those exponents, e to the exponents, then we're gonna get exponential growth. And we're gonna get these exact numbers because we used log of them. That's why we will get, because we used log of them in the linspace. So that's why here in frequencies, we are doing the same thing. So first we have minimum frequency. So we take log of the minimum until log of the maximum, so the ending frequency, which is going to be 1 to 1000 by default. And then we put it through linspace to create exponents. And then we exponentiate with those exponents. I also forgot to say that the amount of these exponents we create is embedding dimension divided by 2 with integer division. So we'll look further. So this would be our number 6. So for example, in our example, that would be our number 6 here, 6 exponents. So we'll see why embedding dimension divided by 2. But before we talk about embedding dims, let's just ignore this and consider this a number. Just look at, so let's see the first, this full line. So we just have frequencies, torch.exp, torch.linspace. We have the same thing that I just explained. And if I do this, we get the same numbers. Now they are a bit, we have only 4 numbers here. So now linspace is gonna create 4 equally distanced exponents as opposed to 8. So these numbers in the middle will not be same, but these beginning and ending are 1 in 1000. So our exponentially growing array is 1, 21, 464 and 1. Oh, this is 10,000. Sorry, this is 10,000. So now we understand this, but let's understand the entire class. It's not that difficult.